If you imagine two lines, the angle between them, theta, what does it actually represent? Well, the angle is a measure of the alignment between the two lines. So, as the angle is decreasing, the lines become more aligned with each other or even fully overlap. However, as the angle increases, the direction of the lines becomes more different and they move into different directions. So sine and cosine, they are similar measures of alignment, but they work on a normalized scale. So basically it takes all the various values an angle can take and then puts it on a specific range, which I'm going to explain in 1 second. But as you know, cosine can be found by dividing the length of the adjacent side by the hypotenuse. And similarly, sine can be found by dividing the opposite by the hypotenuse. So this makes sense then that as sine is increasing, so as sine of a value is getting larger, what's happening here is that either the hypotenuse is getting smaller or the opposite side is getting larger. The hypotenuse generally we consider it constant, so in this case this value would be getting larger. And so if this length is getting greater, what is happening to the triangle here? We can see as the opposite end is getting greater, the alignment between these two vectors is decreasing. They are less similar to each other, so they are moving apart from each other as the opposite side is increasing in length, which corresponds with an increase in the angle. So that's very easy to see now that as the angle is increasing, sine of an angle is also increasing. And so they both measure basically the same thing, but the reason why sine is useful instead of just using the angles to represent the alignment is that it's normalized. So this is a division, and the highest value a division can ever take is 1. You can't go greater than 1 unless the hypotenuse starts to get really small or the opposite side tends to get really large, but you can't have that in a triangle. You can't have a triangle where the opposite side is greater than the hypotenuse. That's you would need an angle of more than 90. In the case that theta is actually 0, our triangle is going from this to this and then basically just entirely overlapping because there is no difference. In that case, our opposite side is 0, because obviously it keeps getting smaller until it basically disappears. And so finding sine of 0 would then give us, let me adjust this. Finding sine of 0 would then be literally 0 over the hypotenuse. So then this would give 0 as a result. But if you're having trouble to really intuitively understand or visualize how dividing 0 by another value works, there's a different way to approach it, and that's by using the concept of limits. So we can say the limit of sine approaching 0, so as sine keeps getting smaller and smaller and smaller and smaller and smaller, until it becomes 0.1, 0.0001, and then 1 times 10 to the power of negative 100. Once it gets this small, we can say it's approaching 0, it's getting to 0. At this point, the limit of theta approaching 0, our opposite side is also approaching 0. And as these two things are approaching, so they're not exactly 0, but they're approaching 0, they're getting so small that it's essentially the same as 0. As these two values are approaching 0, sine of theta is also approaching 0. If you have 10 divided by 5, that's 2. 1 divided by 5, that's 0.2. 0.1 divided by 5, 0.02. So as this numerator with a constant denominator, as the numerator keeps getting smaller and smaller and smaller and smaller, the output keeps getting smaller and smaller and smaller and smaller until it equates 0. When the hypotenuse and the adjacent side perfectly align and theta equals 0, at this point there is no disalignment, and sine is a measure of disalignment, so sine is 0. And conversely, when you have the maximal length of the opposite side equaling the hypotenuse, there is maximal disalignment, so sine equals 1. And if you're having trouble visualizing a scenario where the opposite side is the same as the hypotenuse, let me draw it for you. So here we have a right angle triangle, and here we have the hypotenuse, the adjacent side, and the opposite side. And so if we imagine this angle keeps getting larger, and as a result, the opposite side keeps getting larger, what we end up with at a constant hypotenuse length is that this keeps going up and up and up and up and up and up, up, and the meeting point of this keeps going further and further away. So the point where they converge is further and further away. It's getting so far away, but eventually they do, because all lines that are not parallel do converge at some point. Okay, I didn't draw the right triangle very well, but you can imagine this, and then let's say here theta is 89 degrees. And so at this point, the hypotenuse is almost the same as the opposite, because these angles are almost the same. So the point at which they meet is so far away that it basically requires the same lengths of both of the sides. But if you want to imagine 90 degrees, okay, that's getting a bit complicated now, because you cannot have a triangle with both 90 degrees. Now you just have a square. So that's kind of one of the weaknesses of viewing angles through the lens of triangles, because you can't really represent all of the angles in a right-sided triangle. So you kind of just have to ignore it. And I'm gonna come back to it later, but there's a different way to view it, aka the unit circle. But in essence, you could apply limits again. So we could say as theta is approaching 90 degrees, our opposite side is approximating the hypotenuse. And hence, this would be 1. This kind of shows you that it takes all of the different angles that theta can take, and it normalizes it onto a scale from 0 to 1, where 1 indicates the greatest disalignment and 0 indicates the least amount of disalignment. And this can be useful because we can use it as a scalar for vectors, which I'm going to show in 1 second, or you can use it for a lot of other reasons, and I'll show you why. Now, conversely, cosine can be found by dividing the adjacent side by the hypotenuse. And so we previously established that sine is a measure of disalignment. Cosine is the opposite. It doesn't stand for disalignment, it stands for alignment. This is something that you can try yourself. You can try to prove that cosine of 0 equals not 0, it equals 1. And cosine of 90 degrees equals 0, as opposed to sine, which would equal 0 here, and sine equals 1 here. And conceptually it makes sense because they're kind of standing as opposites to each other. So when we have 0 degree displacement, aka they're parallel lines, this is the greatest amount of alignment, which means that the measure of disalignment is low and the measure of alignment is high because it's perfectly aligned. But you can try to use limits to prove these two cases. This begs the question, what is the point of having sine and cosine when they all describe the same thing and also the same thing that angles describe, because they are all just describing how much two lines are close to each other, aligned to each other. So what is the point of having these when we already have those? And the answer is that these give us formulas that we can use to find out the lengths of the other sides of the triangle or to find the angle. So we can use the angle as a measure of alignment, but these functions really help us to explain the relationship between all of these factors, and then if you need to find one of these, you can actually do it with these formulas. But there's also another very common application, which is to use these as scalars for vectors. So scalars are basically things that change the magnitude of a vector. So as you know, a vector is a value with direction. So you will always see it sort of written like this or like that, and the vector will have a little hat on it. And this basically means, okay, this is 10 10 kilograms, but in this direction, as opposed to another direction. And that's really good for classical mechanics because you often have things moving in a certain direction and you need to incorporate that in your calculations. And sometimes you want to change the magnitude. So a vector will have a magnitude and a direction. And if you want to change the magnitude, then you can use a scalar and multiply it by your vector. So that would just be like 2, and then you'll have 20 kilograms in this direction. A scalar is just multiplying any sort of constant value without direction. I'm going to give you an example of how sine and cosine are used as scalars. So imagine you have a box and you want to push it in a direction. So as you're pushing the box, oh my god, let me redo that. So as you're pushing the box in this direction, the force that you're applying is Fma. In this case, that is mg because we have gravity acting on the box. As you're pushing like this, you will have a force vector and a motion vector. So the force vector is the direction that you're pushing in and how much you're pushing, which is given by the force. And then the motion is just the direction of the box. And so in this example here, they are perfectly aligned. The force vector is the same as the motion vector. So you're pushing in the same direction as the box is moving. And this is great. This is perfectly efficient. You're using all of the force, all of your energy is directly being translated into the motion of this box. But now imagine they were not aligned. So let me draw it again. Now I'm gonna do a view from the top. This is the box. Here's you pushing. And so you're pushing in this direction, but imagine you were pushing from the side, but you still wanted the box to go straight. Now what we have here is a misalignment in the vector. So here's the motion vector. Here is the force vector. As you're pushing here, part of your energy is being directed into this motion. And this is not the motion that we want. We just want it to go straight. All of the force and energy that you put into creating this movement, that is unimportant. We don't want motion here, we only want motion here. So your force vector can be decomposed into 2 different vectors. So we have one vector here going in this direction, that is Fy, and in this direction, that is F of x. So as you're pushing at an angle, it can be said that the force you're applying is equal to the force that you're applying in the x direction and in the y direction, because you could push it like this once and then like that and it would be here, or you could push it like this. So F is equivalent to Fy and Fx. We only want F of y, we only want movement in this direction. So F of x is lost. It's inefficient. You're being inefficient by losing this force vector, and you might think, well, in real life, if I'm pushing in this direction, then the whole box will move this way. But let's just imagine that there is a wall here, and that it can only move in this direction. But regardless, once you're pushing at an angle, you're losing energy. The force that you're putting in here doesn't directly translate into this motion. It's also this little dissipated energy that becomes lost. So in this case, when you're pushing at this angle, F equals mg as always, but how can we show that there is energy loss, so that you need more force to move the box in this direction because we are losing all of this. So you can adjust the formula actually by dividing by cos of theta, this theta. You have the movement vector and you have your force vector, and as the force vector is becoming more disaligned with the movement vector, you're experiencing more loss of energy, and you need to subsequently increase the force that you're applying onto the box. So we can say that as theta is increasing, our force must also increase for the same movement. And we also see that as theta is increasing, cos of theta is decreasing, because remember, cosine is measuring how well aligned they are, so if they are less aligned, then it will be less. So if we visit this formula and plug in some values, let's say the box is 10 kilograms, and let's round gravity up to 10. In a perfect world where we have cosine of 0, we are dividing 100 by 1, which is just 100 newtons. So this would take 100 newtons of force. But if we say that our theta is 60 degrees, so we're 60 degrees away from alignment, then we will have 100 divided by 0.5, which equals 200 newtons. So just by moving to the side by 60 degrees, the amount of force we need to apply has doubled. You now need double the force to move the box. And so in this scenario, here it's so useful to have cosine, because cosine, remember, it's normalized from 0 to 1. And so in a perfect scenario, it doesn't influence the formula. But if we are experiencing loss of energy or some sort of disalignment, then we have all the values in between up to 0 that can modify our formula to adjust for the amount of energy lost. So remember, force here is our vector, and cosine, that's our scalar. It is a non-directional value that modifies our other formula. So it's super useful in this instance, and also in a lot of other classical mechanics you will see it. For example, very often you will see it pushing a box on an incline, because you have all sorts of triangles going on here, and gravity's going here, but also gravity's going there, and then here you have a normal force, and then here you have the resulting vector, and yeah. So there's a lot of triangles everywhere in classical mechanics, and cosine and sine are absolutely super important. Okay, I want to visualize something. So we have this right-sided triangle with some angle. If you go through all the angles from 0 to 90, or I suppose 89 and 1, then you would end up with one triangle like this, one like that, one like this, and one like that, and one like that. And look at what you've created here. This is a half circle. Every point where the hypotenuse and the opposite side intersect, you will map a perfect half circle. So this is from 0 to 90. And now, just do the same thing on the other side. If you do the same thing here, okay, I drew this one worse, but if you do the same thing just backwards, just mirroring it, and then if you do it again and again, you'll end up with a circle as you're going through all of the different angles. And so you're starting here with 0, you're going to 90, and then this is the same as going 0 to 90, or as going 0 to 90 in this direction, because you can move the triangles around in all sorts of ways. So this is essentially 180, because this is just 90 more angles. And then here you have 270, and here you have 360, because you have all of these angles. And so this goes back to the concept of viewing angles as not just alignment, but also rotation, because you can rotate all around in a circle for all these different angles, and you can draw all of these triangles also for every angle. And because you can put all of these triangles in the circle, you can actually do a lot of very interesting math using the circle. And so to simplify the math, by convention, people have sort of agreed that the radius is equal to 1, and so the hypotenuse is equal to 1, because the hypotenuse is going into this distance. And so this is just to simplify the math, because I'm going to show you right now. Since this is a grid of y and x, you can have all sorts of different points of x and y, of course. And also here across the half circle, each point will be a point of x and y. And this is going to get really interesting because, spoiler, x can be represented by cosine and y by sine. And for a long time I didn't know why this was. I just sort of accepted it, and I didn't think about why exactly you could do this. But it's actually super cool, because I want you to think for a second back to the formulas for cosine and sine and the fact that there is a triangle in here, and try to understand why x can be represented by cosine and y by sine. I'm going to give you a minute just to think about it, maybe draw it on paper. Okay, so back to it, I'm going to show you why. So if we have this triangle here, the hypotenuse equals 1, this is the opposite side, and this is the adjacent side. Well, as you see, the opposite side, this is just y. And the adjacent side, well, this is x. So cosine of an angle is given by this, which in our case is x over 1, which is x. Perfect. And sine is the opposite side over hypotenuse, which is y over 1, so it's y. So that is why if you have this circle with a radius of 1, you can say that x is cosine of whatever angle it is at here, and that y is represented by the sine of that angle. And you could also do it with a radius that's not 1, but then the math gets all sorts of wonky, and then, yeah, it's not simple at all at this point, so that's why nobody does it. Okay, so just to recap, what you have now is a circle where the center point is 0, 0, and the radius is 1. And both of these are just by convention. It just makes things easier. There's not really a specific reason why they are that. It just makes the math simpler. And ta-da! This is the unit circle. The main big reason why the unit circle is so useful that will be presented to you in school is probably just to help you remember the values of sine and cosine, because you will be expected to memorize all these different angles. And I think this one is 30, 45, 60, and then you will be expected to remember the x and y coordinates. So for 30 it would be, for example, what is it? I think it's that. Wait, let's fact check. Let's fact check together. So y is sine, and sine measures this alignment. So sine of 0 is 0, and sine of 90 is 1. And we are more aligned here than at 60. So actually this is correct, because this translates to roughly 0.8, and this is 0.5. So here sine is smaller than cosine. On the other hand, 60 is the same, but the opposite. And then the angle of 45 is this. And this basically is mirrored here, 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 and here, here. That's the same. So that is why you will probably see the unit circle to help you remember all of the different values for sine and cosine for different triangles. But there's actually a much better reason why the unit circle is so important. The unit circle is a direct connection between triangles and circles. So it gives you a very good visualization of how the movement of these parallel lines within a triangle is directly related to the movement of a circle, because as these values are all changing, you are creating a circle. So you're creating this rotational movement. Let me explain it to you more thoroughly. Let's use sine again as the example. So sine of 0 will be very small, and then as it approaches 90, it will become bigger. So sine is the y value, so sine is starting out small here, and then it's getting bigger all the way to 1, so it goes from 0 to 1. And then here, we're flipping our triangle, so as we are increasing the angle, technically we're decreasing this angle here as a result. So increasing the total angle, but decreasing this little angle. What we see here is that it's the reverse of this. It's going in the opposite direction. So first we go from 0 to 1, and then we go from 1 to 0. And then you flip that on horizontally, then you will go from 0 to 1, and from 1 to 0 again. So from 0 to 1, and from 1 to 0. So what is happening here? It's going up, it's going down, it's going up, it's going down, up and down, up and down, up and down. And now we have oscillations. So that's why the functions of sine and cosine oscillate. When you map sine or cosine of x on your calculator, you will get exactly this oscillating function, because that is what it does. Sine goes up and then it goes down. And the same is true for cosine. So cosine is the x value, so I'm scribbling a lot here, but I'm almost done. So x value, first it's high, and then here it's low. It's the opposite. So we're starting all the way here on the x-axis, and then we go all the way to the center, and then we go to the side again, and then at this point we go back to the center. So cosine is the opposite. Remember, it goes 1 to 0, to 1, to 0, to 1. And so it's starting high, it's getting low, starting high, getting low, starting high, getting low. So it's also oscillating, but in the opposite manner to sine. So if I give you this grid of x and y, and you map cosine of x, then we are starting here at x equals 0, and remember, cosine of 0 is 1. So we are starting at 1, and then let's go to x equals 90. Then cosine of 90 is 0. So this has gone down here, and then we will move on to 180, where cosine of 180 is again 1, but it is -1. Remember, unit circle, we are now here. So remember, +1, -1. Now we are at -1. And then this keeps going up and down, and looping and also in the other direction. And that's why you have a wave function from cosine. And sine is of course the same, but remember that it's sine of 0 is 0. So we are starting here, and then sine of 90 is 1. So it's starting here, and then it's going up, and it's going to 0 again, and it's going down to 1, and then it's going up again. So it's not entirely displaced, it's still similar. It's not, opposite, but essentially, value-wise, it is kind of opposite. So it's, sine is basically cosine plus 90 or minus 90, because it's just this sort of little displacement here. And look at what I did just now. I just made a formula, I just made a function. I just made a wave function. And so that is why you will see sine smack dab in the middle of the core wave equation. So this is a very big sort of wave equation that models waves, and it will tell you y at x and a given time point, and all of these other values that will move it left or right, whatever you want, or also the amplitude, the frequency, the wavelengths, all of these things, they are modeled in here. But the core of this function is sine, because sine is already modeling a wave. And then, for example, a here, this is a multiplier. This gives you your amplitude. So if you multiply by 10, well then it's going to be 10 times larger. Or if you're adding things and removing things, then you're moving them left and right. So these are all modifiers to the formula, but the very core of this is sine. So cosine and sine, they are inseparable from waves and oscillations, and that's because you can find them in a triangle, and triangles are connected to circles and rotation, and oh my gosh, it's all so cool. Everything is so cool. It's all connected.